parametric curve construction. Often in computer graphics we want to create some kind of smooth curved lines. So here we have two parabola, this one and that one down here. And these are combined in a way where if we take the segment along this parabola from point A to B to C on the first parabola and then continue on the second parabola until point D, then we get this nice smooth curve here. To create the curve, we want to define it somehow. Now one way to define it is by its constraints. So in our example case here, we wanted our function to have value 3 when the parameter is 1. So at x1 we have 3. Then we wanted it to have value 1 when x was 2. So at x2 we have 1. And then 1 also at parameter 3. And these were the three constraints we could define for the left parabola. Now for the right parabola, we also have the same constraint that it should equal 1 when x is 3. And also it should equal 2 when x is 5. But we also had another constraint. We had a constraint on its derivative. So to create this smooth transition here from one parabola to another, we wanted the derivative of the second parabola at this point here, called the not point, to equal the same value as the derivative of the left parabola at that same point. This just happened to be 1, so our third constraint for the right parabola was that the derivative of it at x3 needs to equal 1. So for writing these things out, we have this quadratic function, these constraints. At 1 it should have the value 3, at 2 value 1, at 3 value 1. So 3 constraints, we have 3 unknowns. So we don't know what a, b and c are because we're looking for this quadratic function. We have only said that it needs to pass through these 3 points, but just from these constraints we don't yet know what is the function. Of course, a couple of slides back we had this function here, but to come up with this function, what is a, b and c? What is that parabola that exactly passes through these 3 points? We create this system of linear equations from our constraints and solve it, and then we get the values for a, b and c, and that's gonna be our parabola. A similar thing happens with g, except now one of these constraints is on the derivative instead of the location. Now what we just did is we actually constructed a spline. So a spline in computer graphics is one or many connected curves. So right here we have actually 2 different parabola, but we're creating a spline where we sample from the first parabola until this point, and then from the second parabola for the other half of the spline. And we could continue. We could add new parabola here and continue sampling from the next and the next and the next parabola, and this entire structure would be a spline. Now splines have this property called CN smoothness. So this says that the nth derivative is continuous everywhere on that spline, and that spline is also Cn-1 when n is more than 1. We'll see examples of this later on, but if we have this smooth transition here, this means that the first derivative is continuous, doesn't have gaps, or the spline doesn't change the direction very suddenly. It doesn't have a corner there, so that would be a C1 spline. Later on we will see some parametric splines, and there we can also talk about this G smoothness, so this geometric smoothness, which says that the derivative can have sudden jumps in the magnitude, but not the direction. And we will see a few examples of that later on. But coming back to the C smoothness class, well, if we have C0, this means that the spline itself is continuous. The zeroth derivative, the function itself, it needs to be continuous. For example, here on the left, we have this continuous spline. But on the right, this spline goes here, and then it suddenly jumps to another location and continues from there. So this is not continuous because there is this hole in the spline. Next we have C1. So this means that the first derivative, the speed, is continuous. So on the left we have this nice spline, and if we find this derivative, well, that's gonna be this function here. So on the left here the spline is decreasing, our derivative is negative, here it goes to 0, and then the derivative becomes positive and then becomes 1, and you can see that the spline is increasing at the rate of 1 unit. But on the right we have this example here where the spline is this red line, and the speed, well, its derivative we can see that this derivative has this jump here, or this gap. So over here we have derivative 0, which means that the spline is not changing in value, but then suddenly it starts changing by 1 unit. So the rate of change goes to 0, and then it suddenly becomes 1, meaning that there is gonna be this sharp corner over here. This spline is not C1 because there's a hole in the first derivative. We can also look at the C2 smoothness. So this means that the second derivative, the acceleration, is continuous. So on the left we have this nice spline, we can find its derivative, we can find its second derivative, and we can see that there is no hole in the second derivative. So this is nicely a C2 smooth spline. But on the right we have a bit different spline, and if we find its speed and its acceleration, then we can see that this acceleration has a gap, a sudden jump from one value to another. This causes a sharp change in speed, and while the spline looks smooth, it's actually just C1 smooth and not C2 smooth here. Usually in computer graphics, C1 or C2 smooth splines are enough. And here's another example with our parabola. So if we take two parabola and connect them like this, so that the left parabola has constraints that it needs to pass A, B and C, and the right parabola has the constraints it needs to pass C, D and E without the constraint on the derivative, then there's gonna be a sharp corner at the point where they join, called the not point, and that spline, this entire object, is not C1 smooth. Now these parabola are all nice and well, but actually in computer graphics we want parametric curves. So we want a curve where we can input some value t, which would vary from 0 to 1 for example, and that we would get out points on the curve. So this function would give us out x and y pairs. That would be good for generating points on a curve and making any kind of 2D or 3D curve. For example, this curve on the right here, you cannot have this with your strict mathematical functions like parabola, because one x would have multiple different y coordinates. So this is a function of t that actually outputs different x and y pairs. So it can output the same y given different values of t. Now there are some parametric shapes you already know. For example, we learned the line equation. So if we want to make a parametric line, we can have a point on the line and a direction vector. And if we take that point plus some parameter alpha times the direction vector, then we will get points along this line. And we also saw a triangle. So if we take three vertices, A, B and C, and we take this convex combination of those, then these coefficients here, alpha, beta and gamma, they can be the parameters of this function. Now it turns out that the triangle could also be represented with just two parameters, but for simplicity here we use three that we already saw before. And from high school you might have seen the parametric equation for the circle. So the points on the circle will be radius times cosine t for the x coordinate and radius times sine t for the y coordinate. And you input different values of t and you get points on that circle. So basically our problem comes down to finding the vector coefficients for a function, let's say a quadratic function, a2, a1 and a0. And this function has this one parameter called t, we can also name it time, that goes from 0 to 1. And we can create different degree polynomials. So a cubic function would have a3, a2, a1 and a0. So 4 coefficients that we're looking for. Now fixing the degree of the polynomial is just the first step. We want to also specify the constraints. Should our polynomial pass different points, or should its derivative be a very specific value for certain values of t, and so on. So let's see how we can make a quadratic parametric curve. So we have this quadratic function, a2 times t squared plus a1 times t plus a0. Just a regular quadratic function, except that now the parameter is this t. And our coefficients here are actually vector coefficients. So in 2D, all our a's here will be two-dimensional vectors. If you think more about this, then this quadratic parametric curve actually has two quadratic functions. One for the x coordinate and one for the y coordinate. But they're just encoded in this one row. So we want to constrain this function and its derivatives. A quadratic will have three constraints. There are three unknowns. So 3 is the maximum number of constraints we can have. If we want more constraints, we can use a cubic function. So a cubic function would have 4 constraints because there are 4 unknowns. And the same thing works exactly the same in 3D, only that in 3D we have 3-dimensional coefficients. So let's construct this 2D quadratic curve. And let's take the same points A, B, and C, so 1, 3, 2, 1, and 3, 1 that we had before. Now let's call them P0, P1, and P2. Those will be our control points, or sometimes they're also called parameters. And our constraints would be like this. When we start the curve, when t is 0, we are at this first point. So we are starting our curve here at P0 at 1, 3. That's gonna be our first constraint. The second constraint is that when we're halfway along the curve at t equals 0.5, then that curve has to be at P1. How does it get there? We don't know. We just say it has to be at P1 when we input t equals 0.5. And lastly, when we end the curve, when t equals 1, we want it to end at P2. Again, how it gets there, we don't know. It comes somehow from P1, but when t equals 1, the value needs to be P2. So these are our three constraints. These P0, P1, and P2, like I said, they're called control points or parameters. So let's write out our quadratic function. So here we have this a2 times t squared plus a1 times t plus a0. So when t equals 0, all of these values here will become 0 and we just have this a0 here. When t equals 0.5, well, this is gonna be 0.5 squared and this is just gonna be 0.5. And when t equals 1, when here we have 1 squared and then 1. Now these three equations and these values that we have here, we're going to write out as a matrix. So we can write out these constraints as this matrix that actually specifies the constraints times this vector of our coefficients that we're looking for, because we don't know what kind of a quadratic actually satisfies these constraints. So these a0, a1, a2, this is the vector of unknowns, and this must equal the vector of our control points. Now let's simplify this a bit, because of course anything to the power of 0 is gonna be 1, 0 to the power of 1 is gonna be 0, and so on. So our matrix actually looks like this, and our entire equation like that. Now this matrix is called the constraint matrix, because this kind of specifies the constraints that we had. Then we have the vector of unknowns and the vector of control points. And we can write this out as C for the constraint matrix times A for the vector of A's equals P, well, the vector of our control points. Our goal is to find A. So when we have C times A equals P, we can just multiply both sides from the left with the inverse of C, resulting in the inverse of C times A is the inverse of C times P. Well, this left part here cancels out, and we see that this vector of unknowns actually equals another matrix, an inverse of our constraint matrix, times P. This B here, which is the inverse of the constraint matrix, is called the blending matrix or the basis matrix. So to find our coefficients for our quadratic parametric curve, we just have to find P and then multiply our blending matrix P with our vector of control points P. When we write this out, well, we get that A0 equals B00 times P0 plus B01 times P1 plus B02 times P2, and similarly for A1 and A2. So when we look back at our quadratic function, we had these three terms. We have t squared, t to the power of 1, and well t to the power of 0, which is just 1. And we have this A0, A1, and A2 here. This is just your regular quadratic function, except that I reordered the terms starting from A0 to A2. Previously we had the quadratic term as the first term. So just a moment ago, we found out how to calculate A0, A1, and A2. So it was this. A0 was this combination here, A1 was this combination, and A2 was this combination. So it's specific elements from the blending matrix multiplied with the control points. Now let's reorder these terms. So we're gonna pull out everything that is multiplied with P0, and also everything that is multiplied with P1, and everything that's multiplied with P2. So basically we have this equation here that is multiplied with P0 plus this equation that is multiplied with P1 and that equation that is multiplied with P2. Now that we have reordered these terms, we can see that our curve is actually going to be some combination of the control points. So we take some amount of P0, some amount of P1, and some amount of P2. What amount exactly? Well, this will depend on the t and of course the blending matrix. But overall, we can actually group these equations here into functions. We can say that these are blending functions. So this is exactly what we had before, except that I just name it now a blending function 0, that is a function of t, blending function 1, that is a function of t, and blending function 2, that is a function of t. And we're just using these to blend together the control points p0, p1, and p2. And of course down here we can also simplify, so t to the 0 is 1, well this is just t, so we can write these out as p00 plus p10 times t plus p20 times t squared. Again, t is our parameter, and these are just elements from the blending matrix. So we can write out our curve like this, and in our particular example, this was our constraint matrix. If you remember, we had these 1s and 0.5 and 0.25 here, and we can find its inverse. The inverse of this specific constraint matrix is going to be on the right here, and this is going to be our blending matrix for the curve that passes through these 3 points in a way that we specified. And because of the way we rearranged the terms before, the coefficients in the blending functions are actually rows of this matrix. That is also why it's sometimes called the basis matrix, because they're kind of basis functions for that curve. So we can read out the blending functions from here. Blend 0 is going to be this 1 minus 3 times t plus 2 times t squared. Blend 1 is gonna be 4 times t minus 4 times t squared. And blend 2 is going to be minus t plus 2 times t squared. Exactly these coefficients from these rows that are multiplied with t to the 0, t to the first, and 3 to the second power. We can take these blending functions and fix some p0, p1, and p2 and get our nice parametric curve. And that curve looks like this. So here we have this blending function 0, exactly this 1 minus 3 times t plus 2 times t squared. Then we have blending function 1 and blending function 2. And now we are varying t. So t goes from 0 to 1, and when t goes from 0 to 1, these blending functions all take a different value. When t is 0, you can see that the first blending function is 1, second is 0, and the last one is also 0. This means that we are taking p0 times 1, 0 times p1, and 0 times p2. Let's say t equals 0.5, then all of these blending functions are 0 except the middle one. And when we have t equals 1, then only the last blending function is 1 and the rest are 0. And in the middle, there's going to be some combination of all of these control points. When we add those together, we get this nice curve here. So it starts from p0 when t equals 0, right here. It goes to p1 when t is 0.5, and finally to p2 when t equals 1. Exactly like we wanted. We can change these control points in any way we want. So we could move this p0 to be here, we can move this p2 to be here, or p1 here. No matter how we arrange them, we're still going to get a curve that is going to start at p0, move through p1 at t equals 0.5, and end at p2 when t equals 1. So we just created a quadratic curve to interpolate or pass through our control points. We can use exactly the same construction for cubics or any other higher order polynomials, and we can use exactly the same construction with also other constraints, for example the constraint on the derivative. So to recap, first of all, choose a degree for the polynomial, a quadratic, cubic, any degree that you deem is necessary. Secondly, decide on the constraints. Do you need the curve to pass some specific values? Do you need its derivative to be a specific value at a certain location, or maybe the second derivative has a constraint? Then create the constraint matrix. You just write out the equations for the constraint and create a matrix from that system. Next, find the basis or blending matrix by taking the inverse of the constraint matrix. And then you read out the blending functions from the blending matrix, just the columns of that matrix. And you use these to implement your blending functions, and then you can send in different values for t from 0 to 1, and you will get the curve that satisfies your constraints. With this, you are able to create any polynomial curve that you want. Now in computer graphics, we usually want to use cubic polynomials, not quadratics, because then we have 4 constraints. and 4 constraints are usually enough. For example, we could have constraints, 2 of them for the position and 2 of them for the derivatives at these locations. And we can also construct neat splines that join together smoothly, because cubic polynomials provide 4 constraints. Splines can achieve C2 smoothness. With quadratic polynomials, that will not be generally possible. Now we talked about this geometric smoothness as well. So with these parametric curves and splines, the derivatives are actually vectors. So before we had this line for the derivative when we had these pure mathematical functions, but right now we have these parametric curves, so the derivatives we can represent as vectors. So in the beginning here, this arrow kind of points towards where this curve is traveling to. Mathematically, the x-coordinate of this arrow would just be the derivative for the polynomial we have for the x-coordinate, and the y-coordinate would be for the polynomial that gives us the y-coordinate. But it's more easier to look at them as arrows. So over here, these arrows change their size and direction smoothly. There isn't like a sudden jump at any location, so this curve would be C1 curve. However, with parametric functions, we could have something like this, where there's this sudden change in the derivative's magnitude. So when we approach this point from the left, we are moving with, basically this speed that is represented by this arrow here, like a slower speed, and then suddenly we are now moving at a higher speed. So the magnitude of the derivative, the size of this arrow, suddenly changed, but the direction is still the same. This means that this curve doesn't get this corner here that you would get if the direction also suddenly changes. Instead, it's still visibly quite smooth, except that it kind of gets elongated here quite suddenly. So this we can call G1 smooth spline. So from this video, you learned the Cn smoothness class, which tells us is the nth derivative, and well, all the previous derivatives as well, up until the curve itself, is it continuous. And then we also learned the Gn smoothness. So for parametric curves, the nth derivative could have a sudden jump in the magnitude, but not the direction, and that would satisfy the geometric smoothness class. We learned about these parametric polynomial curves, and how a polynomial's degree affects the number of constraints we can give it. We can set constraints on the location and the derivatives. We learned about this parametric curve construction. So few easy steps, how you start by setting the constraints and then end up finding the blending functions for any kind of curve and any constraints you want. And then, well, we learned about these blending functions. So our polynomial curve will actually be a blend of the control points, and these blending functions behave specifically according to the constraints you set to satisfy these constraints and blend between these control points. We also learned about splines. Well, splines, they're also called piecewise polynomial curves. So we have a larger object where each segment is a polynomial curve, and these are connected. It might be connected in a smooth way, or there could be corners there. It all depends on what kind of a spline you created.